Hello and welcome to my video on the fly-by-wire system of the Boeing 777. Now I realize this is going to be a lengthy video, so if you are interested in a specific topic, just have a look on the index below and jump to the corresponding minute on the video. Now first I'm going to give a little introduction of the fly-by-wire of the 777, then I'm going to address how it is integrated into the desktop simulation provided by PMDG, which is excellent by the way. And next I'm going to be trying out a series of scenarios and comparing how the aircraft responds in direct law and in normal law. This will be done in order to see what the capabilities of the fly-by-wire system are. Finally, I will play around a little bit with some failures, which can be accessed through the PMDG page on the FMC. So, a little introduction on the system first. All of the information that I'm going to give has been obtained from a series of sources, but mainly it's the FCOM Volume 2 on the chapter regarding flight controls, and it's also a chapter on the avionics handbook, which I will link below, chapter 11 on the fly-by-wire system, and the chapter was written by a Boeing engineer. It's very informative, I will link it below. Now I won't go deep into the theoretical explanation, I'm just going to explain the basics. The fly-by-wire system of the Boeing 777 is designed to make the aircraft feel and fly just like a conventional airplane, but with enhanced qualities of flying. This means that the pilot doesn't have to learn to fly again. If the pilot comes from a 737, which is a conventional jet airliner, to the 777, he won't have to learn how to fly again. He can apply all the same principles of conventional flying. It's just that he will feel that the 777 flies very well. It's like if you jump into a car, into a Mercedes S-Class, and you feel how well the aircraft, the car drives. That's comparable to how well this aircraft flies because of the enhanced qualities. Also, not only enhanced qualities, but the fly-by-wire offers a series of protections, which we will analyze in the following parts of the video, and you will see how helpful these protections are. Envelope protections. Now the flight envelope protection of the 777 consists of soft limits, which means that they can be overridden by the pilot. Ultimately, the pilot has full authority on the aircraft. That's Boeing's philosophy. And if the pilot is determined to, for example, fly the aircraft into a stall, he will be able to do so. It's just the aircraft is going to make it very difficult, but won't completely take control from the pilot. So that's on the basic philosophy of the fly-by-wire of the 777. Now how the system works, basically there are 4 ACEs, which are the actuator control electronics, and then there's 3 PFCs, the primary flight computers. Now the pilot inputs a command through the controls. In this case, for example, I'm moving the control wheel, the control column back and forth, and the rudders, you can see them right below, as well as some other systems, but these are the primary flight controls for the 3 axes: roll, pitch, and yaw. Now this is an analog signal that the pilot is generating, and this signal goes to the ACEs. Now the ACEs are basically analog to digital and digital to analog converters. What they do is they send the signal from the pilot digitalized to the primary flight computers. Now the primary flight computers take a lot of information into account regarding the state of the aircraft, the configuration, and a bunch of parameters like, for example, engine thrust, temperature, and so on. and what it does, it enhances the signal. Now, how it does so is out of the reach of this video. It just makes the signal better, so to speak, to enhance the flying qualities of the aircraft. It also implements the soft limits we talked about earlier and the protections. Now, this, so to speak, enhanced signal is returned to the ACEs, and the ACEs are redirected both to the pilot controllers for feel, so that the pilots feel the forces on the controls, and also they are sent from the ACEs to the control surfaces. In fact, they are sent to the actuators, to the hydraulic actuators, which will move the surfaces. So that's basically how the system works. 4 ACEs, 3 PFCs, and now the system has 3 levels or 3 types of law. In normal law, which is, as the name implies, let me move the flight control page here. The aircraft is designed to fly in normal law. Everything works normal as expected. All the PFCs and ACs are working. All the systems are working just fine. And the aircraft has its enhanced flying qualities as well as its protections available. Now, should the PFCs decide that there are failures in the system, or some systems are unreliable, they may revert to secondary mode. Now, secondary mode is a degraded mode. In secondary mode, there's no autopilot, for example. You cannot use the autopilot in secondary mode. There is no thrust compensation to correct asymmetry. There is no turn coordination. There is no, and a series of other protections don't work. But the primary flight computers are still online, so the ACEs are still communicating to the primary flight computers. Now, the lowest level is the direct low. In direct low, what happens is that the PFCs are not working all together, are completely disconnected, and the signal from the pilot goes to the control surfaces directly through the ACEs without going through the PFCs first. Now, in direct low, there's no protections whatsoever, and as the name implies, the signal of the pilot goes directly to the controls, meaning the pilot can fly the aircraft like a conventional aircraft, really. Now, on the overhead panel of the 777, the primary flight computers can be accessed here and disconnected, all 3 all together, like so. And as you can see, now we are flying in direct mode, in direct low. We will analyze the implications of flying in direct low later on in the video. Also, you can see the ECAS warning, primary flight computers, and a series of messages, a status message as well, caution light. But the truth is that the aircraft can be flown perfectly fine just like this. Now, there's also the thrust asymmetry compensation. What this does is, in case of an engine failure, it will automatically input rudder so that the pilot, so that the aircraft doesn't yaw to the side of the failed engine. So let's try that out. Turn the thrust asymmetry compensation off. Disarm the auto throttles. And see what happens if I bring one of the thrust levers back to idle. The aircraft will yaw to one side. If I can manage to move the lever, there it is. And advancing this one. Now the aircraft is jawing to the right, correction to the left. and you can see the heading of the aircraft slowly going to the left. Now in the videos to come we will analyze. Let's turn the thrust asymmetry compensation back on and the auto throttles as well. And now they will automatically align both thrust levers to fly as the aircraft usually should. Now a note of the integration of the fly-by-wire on the PMDG 777. Here on the PFD, on the primary flight display, you can see a blue FBW indication or bug, and this is the trim airspeed, the airspeed the aircraft is trimmed to. Now we will use this feature extensively, and this is not in the real aircraft. The reason being is that in the real aircraft the pilot has feel on the control column, and he can trim the aircraft very nicely until he feels there is no force required on the column, at which point he knows he is in trim. Now, given that in a desktop simulator that's not usually the case, there is no feedback on our controls, PMDG decided to include this help in order to be able to trim easily, to trim the aircraft more easily. Now you see in this case, for example, we are in trim, flying at 250, and the trim is also at 250. Now how the trim system of the 777 works is not exactly like a conventional airplane. On a conventional airplane, when you trim, for example on a 737, by trimming you move the stabilizer. So the trim switches directly command the position of the horizontal stabilizer. Now on the 777 that's not the case. When you trim, what you're doing is asking the aircraft to be trimmed for a certain airspeed, and the PFCs will move both the stabilizer and the elevator in order to have the aircraft stabilized at the trimmed airspeed. So we will compare the functionality of the trim switches both in normal law and in direct law with the PFCs in operative. Okay, I hope you like the video, and see you later. Bye bye. Here we are again flying level at 10,000 feet and 250 knots. So first let me disconnect the autopilot. There it is. You see we are trimmed for 250 or 249. Let's see what happens now if, while leaving a thrust constant at around 58%, we change the trim airspeed. So let me disconnect the auto throttle and increase the trim airspeed to something like 280 knots. So naturally the nose of the aircraft is coming down. The aircraft wants to accelerate to 280, and it's diving into a steep descent. Aircraft passed 280 knots, and now the nose is coming up again, slowly. Eventually this acceleration will stop, and it will become a deceleration. After a couple of cycles, the aircraft will have established itself at 280 knots. Let's put it there at 280. And what's going to happen in the steady condition after the transition is that the aircraft is going to be descending at 280 knots and at a given vertical speed. Now I'm going to cut it here and show you the final steady condition. So here we are again in a steady condition, trimmed at 301 knots. I increased the airspeed a little so as to have a more apparent effect, because at 280 the descent was really shallow at something around 100 feet per minute. Now you see the aircraft is ascending up at about 300-400 feet per minute. And remember, we are having the thrust output of a 250 steady flight condition. Also note that our angle of attack has decreased to 2.2, and that's because of the increased airspeed. So in order to fly in a steady condition without acceleration, but at a higher airspeed, we need a lower angle of attack. In this example, we'll see what happens if we trim down in direct low. So we are level at 10,000 feet, 250 knots, 60% and 1. Let's disconnect the auto throttle. Auto throttle off. Let's also disconnect the autopilot. Autopilot off. You see we are trimmed for 250 right now. Now let me disconnect the primary flight computers. The alarm. And now I'm going to trim nose down for 3 seconds, which is the equivalent of 30 knots in normal low. So 1, 2, 3. The aircraft is pitching down naturally. Airspeed is increasing, vertical speed is increasing, and you see the stabilizer is fixed at 4 units. In direct low, when using the trim switches, we directly position the stabilizer. We don't command a trim airspeed. So speed is continuously increasing and will eventually reach an overspeed condition, at which point the auto throttle will wake up and spool the engines down to idle. There you see the overspeed warning, auto throttles woke up, and they are moving the thrust levers back all the way to idle. Now this is not stopping the aircraft from descending, and it's descending even faster now without the power, and eventually the aircraft will crash into the ocean. So that's it for trimming and direct low. Okay, so in this example we are flying level at 10,000 feet and 250 knots. What we're going to try to analyze is the effect of a thrust increase while remaining the trim airspeed constant. So let me first disconnect the autopilot. There it is, you see the blue fly-by-wire at 249, 250. Now let's first match my hardware to the aircraft throttles. There it is. And now I'm disconnecting. There. Now I'm going to increase the thrust slightly. And what's going to happen is all this excess thrust is first trying to increase the airspeed of the aircraft, and then it's going to make it climb. So the speed is going to enter a phugoid oscillation now. It's going to, first the speed went up, then the aircraft it's raising its nose and the speed will come down. It will come down below 250. There it's coming down slightly below 250. Now the nose is coming down again, and the aircraft will accelerate, and eventually it will reach 250 knots again. Now to be in equilibrium at 250 knots with this thrust, the aircraft is going to be climbing at a given vertical speed. So there you see pretty much it found equilibrium already. At 70% and 1, the aircraft is climbing at around 900 feet per minute. And as you can see by the angle of attack indicator, we are pretty much having the same angle of attack, 3.8, as before, and that's because we are flying steady now, without acceleration. So the lift of the aircraft equals the weight. So let's see what happens if we now close the throttles below 50% and 1, which was the level thrust previously. So first the aircraft tries to decelerate, but because of the pitching moment the aircraft is pitching down and it's going to start a descent now. There it's descending. Aircraft will increase above 250 and then the nose will come up again, and eventually the aircraft will stabilize at 250 knots. There is the speed above 250, 253. Now the nose is racing. And now it's finding equilibrium at 250 and descending at around 300 feet per minute. And again, the angle of attack is 3.8, exactly the same as before, because the aircraft is flying in a steady condition, lift equals weight, no acceleration. Now we will see what happens if we turn the aircraft in direct mode. So let me disconnect the autopilot first. There it is, and now disconnect the primary flight computers, like so. And now we're going to input a roll command through the control wheel without touching the rudder pedals. So let me bring this up. You see the aircraft is rolling, but the rudder pedals, the rudder is not moving, and you see the aircraft is slipping. If you focus on the little sailboat, the base of the boat and the sail are not aligned, indicating that the turn is not coordinated. Now let's see what happens if we try to roll past 35 degrees. Now the sailboat turned amber, but I noticed no force on the aircraft, so to speak, on the controls, trying to push it back to 30. And I can roll all the way to 45, or even 60. In fact, I can roll it over all the way. And fly inverted, just like in the movie Flight. So don't try this at home, please. In this example we will see how the aircraft behaves to roll commands through the control wheel. I won't be using the rudder pedals, just control wheel. So in order to do this I need to disconnect the autopilot, and in this case it's important not to use the autopilot disengage bar, because doing so would inhibit the roll protection of the normal law. So let me disconnect the autopilot and start a turn to the left. I'm not touching the rudder pedals, nose is blowing, so I have to pull a little, but you see the aircraft is automatically compensating for a coordinated turn. So everything goes normal all the way to 30 degrees bank angle. Thrust is also increasing to keep the speed of 250. Now if I try to roll the aircraft even further, the sailboat turns amber, and there you see the aircraft bounced back to 30 degrees. Let me try that again. The amber yellow boat and the bank limit protection in action. So if I was determined enough to roll it further away from 35, I could do so by inputting maximum control wheel deflection. There you see 45, 60, but the aircraft wants to go back to 30 degrees. So if I release the control wheel altogether, the aircraft rolls back to 30 degrees. So let's try this very same experiment in direct law now and see what happens. Okay, so in this example we're going to analyze the response of the aircraft to a configuration change in the form of a landing gear drop. So when we drop the gear, what's going to happen is the aircraft, the autothrottle, is trying to maintain 240 knots, and it will increase the thrust output from 60 to something about 75-80% and 1. And the increased thrust is going to cause a nose-up pitching moment, and this will make the aircraft try to climb. So you will see that the stabilizer trim and the elevator will command nose-down attitudes to contain this tendency to climb by the increased thrust. So let's disconnect the autopilot first. 2 clicks. See, the aircraft is trimmed for 240 knots. Let's drop the gear. Thrust is increasing. The nose is coming up. The aircraft is climbing, and now look on the stabilizer trim and elevator. Elevator is commanding nose down, and stab is also commanding nose down. So the PFCs are containing the attitude change due to a configuration change. Let's see what happens now if we disconnect the PFCs and try this very same experiment in direct law. Okay, so now let's try the same thing of dropping the landing gear, but this time in direct law. Okay, so the first thing I'm gonna do is disconnect the autopilot. Autopilot disconnected. Now I'm reaching up here in the overhead and disconnect the primary flight computers. Disconnect. Come down here again, and now let's drop the gear and see what happens. You see the stabilizer trim and the elevators will remain in the initial condition. Autothrottle is trying to maintain 240 knots, and now you see the aircraft is pitching up because of the increased thrust, and because it's pitching up, it's continuing to lose airspeed, and the throttles are continuing to spool up the engines. So this is a vicious cycle kind of thing. See, aircraft vertical speed increasing, 900, 1000 feet per minute. Thrust is increasing even further, and the pitching moment upwards is increasing because the stabilizer trim is not compensating for the increased nose-up pitching moment. Now we have almost full thrust, and the aircraft is climbing at 2500 feet per minute. Now the speed is decreasing, and it will continue to come down until a stall, or let's see what happens. If the speed comes down enough, this will become a power on stall, meaning the aircraft is stalled even though the power or thrust is on, so to speak. Angle of attack is increasing, and we're reaching the top of the amber zone, which is the minimum maneuvering speed. now it's pitching down again. And speeding up again. But this cycle will repeat itself. I believe the aircraft is going to accelerate maybe to 240 knots, or something like that, to 20. Since the drag is down and we didn't trim for the increased drag of the gear, it's going to pitch up again eventually, and the cycle is going to repeat itself. You see now the aircraft is pitching up again, I think, yes. So that's what happens with the configuration damping of the primary flight controllers, PFCs, primary flight controllers. So let's see what happens on the next example. So in this example we will demonstrate the stalling protection of the envelope protection system. You see we are flying very close to the minimum maneuvering speed at 180 knots. Let's see what happens if we try to slow it down to 160. So the throttles will relax back a little, and the speed is coming down. But the throttles are spooling up again, and the aircraft won't really descend below the top of the amber bar. The auto throttle won't let the aircraft slow down below the minimum maneuvering speed. So right now we are flying the minimum maneuvering speed at 10 degrees nose up pitch attitude, which by the way is the same as the angle of attack because we are flying level flight. By the way, the angle of attack is the angle difference between the nose of the aircraft here and the flight path vector here. So if you're flying a glide slope at a 3 degrees descent angle and your attitude is 3 degrees nose up, then your angle of attack will be 6 degrees. Okay, let's see what happens if we disconnect the auto throttle and try to slow the aircraft down below the minimum maneuvering speed. So I'm going to disconnect, thrust back, auto throttle engaged again in speed. So the auto throttle is now spooling the engines up again and won't let it slow down below 172 knots. So that's a feature of the auto throttle system. In order to prevent it from happening, we have to disarm the auto throttles. So let's see what happens if we disarm the auto throttles and force the aircraft to slow down below minimum maneuvering speed. There you see autopilot is preventing the aircraft from descending. The stab is commanding nose up attitude. The elevator are moving up as well. Airspeed low warning on the ECAS. Altitude, the aircraft is no longer capable of maintaining altitude, as you can see on the FMA, and it will start descending to prevent it from stalling. And the aircraft will continue descending to prevent it from stalling. So let's engage auto throttle again and go back to 180 knots. Now altitude mode is enabled again on the FMA and it will climb to 13,000 feet again. Now let's see what happens if we try to stall it in normal mode. For that I'm going to disarm the auto throttle and disconnect the autopilot as well. There we are, level at 13,000. Going to disconnect the auto throttle, disarm it as well, and disconnect the autopilot. Now, you notice the blue fly-by-wire indication on the PFD, that's the trim airspeed. I'm going to lower the trim airspeed all the way I can, and you see it stopped by the top of the amber band. That's because the PFCs, the primary flight computers, won't allow you to trim for airspeed below the minimum maneuvering speed. So if you want to fly below minimum maneuvering speed, you will have to actively pull on the joke. So as the aircraft is trying to let you know what you're trying to do. So let's reduce the speed by spooling the engines down. Let's see what happens. If we try to maintain altitude while slowing down. Okay, now I cannot pitch nose up anymore, so I have to pull on the joke. I have to pull on the joke, pull on the joke, pull on the joke. Now I'm pulling at maximum joke deflection. And if you can have a look, really the elevators are not maxed out. The aircraft is stalling, but it's descending. So really the aircraft just began to stall. It didn't allow me to fully deflect the elevators up, even though the joke was in the full up position. So let's try that again. Stick shaker activates, and I'm commanding the joke. I'm pulling the joke full range, but as you can see the elevators are not fully deployed. And there's a stick shaker again. So the flight envelope protection system will prevent the pilot from stalling the aircraft, at least fully. So now we're going to try the same experiment, but in direct low. Let's see what happens. So here we are, level again at 13,000 feet, and this time we're going to try to put the aircraft into a stall by disconnecting the PFCs. So first let me disconnect the auto throttle, disarm it as well. Next I'm going to disconnect the autopilot, disarm it, and reach up on the overhead for the primary flight computers. Disconnected, and we have the warning. So now let's try to slow the aircraft down. You see I can still trim up, nose up. This is me trimming, because in direct low the trim switches on the joke, these switches, directly position the stabilizer. So I'm trying to keep my altitude while the aircraft is stalled, and if I fully deflect my ailerons up, you see the angle of attack increasing, and the aircraft is completely stalled. I'm still keeping my joke all the way back. The aircraft continues to be stalled, and the only way to get out of a stall is by pushing the stick forward. The stick or the joke. There it is. This is a very nice complement of the book Stick and Rudder, in which it instructs you that the only way out of a stall is pushing the stick forward. So let's push it back all the way again. Let's see what happens. There we are, stalled again. We can continue to trim up. All the way to maximum trim up. In fact, I don't know what the maximum trim up is. 14. So in normal law, the PFCs won't allow you to trim up this much. Let's reach the full range of trim up on the stabilizer. 1475. Elevator full up, and the aircraft is completely stalled. So that's enough for now. Don't try this at home. So in this final part on my fly-by-wire analysis of the Boeing 777 by PMDG, I'm going to discuss the failures you can program into the simulation through the FMC, through the central FMC. Well, you can use any of the two, but I like to use the third FMC for flight simulator related issues. And of course, the failure programming is a simulator thing, not a real aircraft thing. So you go to the menu, PMDG Setup, Aircraft, Failures, and then down to Flight Controls, third page, Programmed, and here you can navigate through the list of failures that are available at your disposal to play around with. So let's see, for example, what happens if we fail one of the ACEs. There are 4 of them. Let's see what happens if we fail the left one. Execute. So now you see on the multi-function display, out of the 4 ACEs, 1 is amber, meaning inoperative, and the 2 corresponding spoiler panels, which are operated by only by the left one ACE, have failed. That is the 2nd and the 13th spoiler panels. See, everything else is working fine. The aircraft is still flying in normal law. Also, we have a ECAS message on the warning messages, and these require a checklist, but we will continue to fail systems. So the spoiler and auto speed brake means the auto speed brake is inoperative, meaning on landing we would have to deploy the speed brake manually, and spoiler means that at least one or more of the 14 spoiler panels are failing. So let's have a little more fun and keep failing more of the stuff. Let's fail the right ACE. There you see a bunch of other control surfaces failed. The right ACE failed. Still flying in normal law though. Let's fail another one. There it is. Now we are in secondary. Let's cancel the master horn, master caution. So after failing 3 of the 4 ACs, the primary flight computers have decided that's enough. They are reverting the flight control mode back to secondary because there's too many faults in the system to be flying in normal law reliably. But still the aircraft is flyable. You see, we have enough control surfaces to fly the aircraft. So let's now do the non-normal checklist. This will also demonstrate the capability of the non-normal checklist. And let's fire checklist app. Now the aircraft automatically goes to the non-normal checklist page. Let's select the highest one, flight control mode. Condition: the flight control system is in secondary mode. Okay, we know that already. Primary flight computers disconnect, then auto. So let's do that. Disconnect, and then auto. So you see the green check. Flight control mode message blanks. Nope, it didn't blank. Avoid abrupt control inputs. The airplane response is changed by a simplified elevator field and rudder ratio systems. Okay, thank you. Ground proximity flaps override switch override. It was already an override because I was playing before. Note, inoperative items, autopilot in op, envelope protection functions in op. Let's keep reading. Jaw damper is degraded. Manual control inputs are needed to compensate for asymmetrical thrust conditions. Use flaps 20 for landing. Do not arm the speed brake. Manually extend the speed brake. And checklist inhibited, auto speed brake and thrust asymmetrical compensation. These are inhibited because they are included in this one. So there you see the list of stuff that the aircraft is informing us to be aware of. And let's see if it... And let's see from the outside view how the aircraft looks like when trying to fly it. So this is the left wing. You see one of the spoiler panels is working. Now the left aileron is working as well, I believe. Let's look over on the right wing. There you have the right flaperon and one of the spoiler panels working as well. Now the elevators, I believe elevators don't work. The right elevator works, the left one is failed. And if we cycle through the views to have a view of the rudder, there we have a view of the rudder. The rudder is failed as well. It's not responding. But we can control the rudder through the rudder trim, I believe. No, so apparently we have no rudder authority. Now let's see what happens if we fail all 4 ACs. Okay, now we are flying in direct law. And the only thing we can control in direct law is the stabilizer. We can move the stabilizer up and down, but I'm moving the joke and there is no roll control. There's no pitch control through the elevator and there's no rudder control. We can, however, control the aircraft through the alternate pitch trim. See, the stabilizer is moving. And also we would control the aircraft using asymmetrical thrust. So that's the way we would fly the aircraft, with differential thrust and with the alternate pitch trim. So now it's your turn to go ahead and try all of these and play around a little. It's very fun. Just don't try this in the real aircraft, please. And I hope you enjoyed my video on the fly-by-wire of the 777. Thanks for watching.